Okay, section 7.2 is on using a graph to solve a system of linear equations. So if you think about what a linear system represents, it represents two linear equations, and basically linear equations have graphs which are lines. So when you draw the graphs of the lines, what's going to happen? And what do you think the solution would show up as on your graph? So if you think about that, it should make sense to you that when you graph two lines, if it's a point that solves both equations as a solution to both equations, it should show up as a point of intersection. That should be the point that fits both equations. So if we're going to solve a system of linear equations by graphing, we are looking for where the graphs cross over, what their intersection point is. And the x-coordinate of that intersection point should be the value of x in our linear system, and the y-coordinate of that intersection point should be the value of y in our linear system. So we're going to take a look at this first example, and we've done a lot of graphing in chapter 6, so you should be familiar with how to graph each of those lines. Both of these lines are in slope-intercept form, so just to remind you that when they're in slope-intercept form, y equals mx plus b, m is your slope, and b is your y-intercept. So if we take the first equation, y equals a third x minus 2, we know that that has a slope of 1 over 3, and we know that it has a y-intercept of -2. So if we go to graph that line, we would start with our y-intercept of -2 on the y-axis, and our slope of 1/3 would be up 1, right 3, up 1, right 3, or we could have gone down 1, left 3, so on. So basically this would be our first line. Oh, so squiggly, sorry. And then our next equation has y equals -x plus 2, so that would mean the slope would be -1, and the y-intercept would be +2. So we would start at a y-intercept of 2, and a slope of -1 means down 1, right 1. Down 1, right 1, down 1, right 1. So we can see, thankfully, that these are crossing over at a point that I actually plotted on both, because my lines were so squiggly I wouldn't be able to figure it out otherwise. So again, if you were doing this, you'd be able to use a ruler and it would be a lot straighter. So you can see that this point right here would be your solution. And the solution would be 3 would be the x value, and the y-coordinate is -1. And you can always go back and check to see if you did it right by plugging it back into your equation. So if we take our first equation, y equals a third of x, a third of 3 would be 1. Take away 2 would be -1, so that does match the first equation, is a solution to the first equation. Then if we check the point in the second equation, y equals the negative of x, so the negative of 3 plus 2 would be -3 plus 2 would be -1. So again, it's a solution to the second equation, so we know we definitely have the right answer. Example 2, same type thing here, but this one is not written in slope-intercept form. So you can change it to slope-intercept form, which is what I usually do. You could use other methods of graphing as well, but for most of these ones, when you're solving by graphing, I find it easier to use slope-intercept form, plus gives you good practice on slope-intercept form. So the first one, if we isolate the y term, we get 3y equals, bring that x over to the other side, we get a positive x, and the 18 is still positive because it doesn't move, stays on the right side of the equal sign, so it stays positive. And then we would divide everything by 3, and that would give you y equals 1/3, that's understood to be 1/3 x plus 6. So we know the slope of this particular line is 1/3, and the y-intercept is 6. So if we sketch that, we have a y-intercept of 6 on the y-axis and a slope of 1/3. I'm going to go down 1 now. So if I go down 1, I'd have to go left 3 to get a positive slope. Down 1 and 1, 2, 3, left 3 to get a positive slope. So if I connect those, there's my line. I don't have a whole lot of space there to write the other one, but we'll squeeze it down here. So the other one is not as hard to rewrite because the y doesn't have anything in front of it. So if I keep the y on the left side and bring the 2x over, it becomes negative 2x. And the minus 1 stays minus 1 because I haven't changed that. I've left that on the side that it was already on. So therefore the slope is your negative 2. And your y-intercept is negative 1. And if it helps you, slope is negative 2 over 1. So that means you rise to run a 1. Make sure you keep it as a negative slope. So if you start on your y-intercept of negative 1 and count your slope of negative 2, that would be, if I go up 2, I'd have to go left 1. Up 2, left 1. Up 2, left 1. So you can see you're crossing over that same point there again that you used on the other graph. So your solution, I'm just going to use a different color there, the solution would be the ordered pair, x coordinate is negative 3 and the y coordinate is positive 5. And you can check your answer again by plugging it into your equation. If you have a negative 3 for the x, that would be in the first equation, the negative of negative 3 would be positive 3. And then 3 times 5 would be 15, so 3 plus 15 is 18. It works in the first equation. And if you go back and plug in negative 3 into your second equation, 2 times the negative 3 is negative 6. Negative 6 plus 5 is negative 1. And that works in your second equation, so you know you got it right. All right, so these are ones now for you to try, but we'll do them together. So this one is slope. First one is already in slope-intercept form is 2, and the y-intercept is negative 5. Oh. Oh my, the more I work do it, the worse it gets. Okay, and now the bottom one you're going to have to rearrange a little bit. So this would be 3y equals negative 2x plus 9, because you brought the 2x term over. And then you're going to have to divide everything by 3, sorry. And that's going to give you y equals negative 2/3 x plus 3. So that equation would have a slope of negative 2/3 and a y-intercept of 3. So if we graph the top equation, we had a y-intercept of negative 5 and a slope of 2. So that would be up 2, right 1, up 2, right 1, up 2, right 1, up 2, right 1. It's the first equation, and the second equation had a y-intercept of 3 and a slope of negative 2/3, so down 2, right 3. And the solution would be the point of intersection, which would be right here. And that would be coordinates 3 for the x and 1 for the y. And if you check your solution, 3, 1 into your given equations, if I plug a 3 in for the x in the first equation, I get 6 take away 5, which is 1, so it works in the first equation. And if I plug it into the second equation, you get 2 times 3 is 6, plus 3 times 1 is 3, 6 plus 3 is 9, so I know I did it right. Next example, again, we're going to have to change those to the proper form. So for y equals Then you bring over your x, which is a negative on the left, so when you bring it over, you add 3x to both sides. It's going to be positive on the right-hand side of the equation. And then you got to divide by 4, which is going to give you 3/4 x plus 5. And that would mean your slope is 3/4. And your y-intercept is 5. So just graph that one first. So there'd be y-intercept of 5. Slope of 3/4, so I can't really go up any further, so let's go down 3, 1, 2, 3, which is in the negative direction, so I have to match that with a negative run of 1, 2, 3, 4. And not a whole lot of points I can draw for that one, so we'll just connect those. And then the other graph, other equation, we want to get the y by itself, so we have negative 2y. We bring the x over to the other side, it's going to be negative x minus the 8 that's already there, and then we're going to divide everything by negative 2. And then that's going to give us y equals 1/2, because negative over negative becomes positive, so that's understood to be a half x, and plus, again, negative over negative is positive, so that's going to be plus 4. So our slope is going to be a half, and our y-intercept will be 4. So if we sketch that graph, the y-intercept is 4, and our slope is positive a half. So that would be up 1, right 2, or down 1, left 2. Down 1, left 2. So it's going to cross over right there. So our solution has coordinates negative 4, positive 2. And again, if we check, it's a good idea for me to check here because my graphs are so squiggly. But if I plug in negative 4 in for the x, I get negative 3 times a negative 4 is going to be 12, plus 4 times the y is 4 times 2, which is 8. So 12 plus 8 is 20, so it works in the first equation. And then if I plug it in the second equation, negative 4 for the x minus 2 times 2 is 4. So negative 4 minus 4 is negative 8, so I know that it's correct. So we try the next two examples. This one is not too hard to rewrite. You just get the y by itself, and then it's negative 2x plus 5. And that would be a slope of 2. And a y-intercept of 5. Sorry, a slope of negative 2. And then the next one would be a little bit more to rewrite. That would be 2y equals negative 4x plus 6. And then you divide everything by 2. So you get y equals negative 2x plus 3. So this is going to be a slope of negative 2. And this is going to be a y-intercept of 3. Now you might already notice something, that both of these lines have the same slope. So you should know something about that, because we did that in chapter 6. But if not, you'll see it now when we graph it. The y-intercept is 5 for the first one, and slope is down 2, right 1, down 2, right 1, down 2, right 1 to give a negative slope. And then when we graph the other one, we have a slope of negative 2 and a y-intercept of 3. So 3 and then down 2, right 1, down 2, right 1, down 2, right 1. And you can go as far as you want, but those lines are never going to cross, because you should know that if they have the same slope, it means they're parallel lines. So therefore parallel, I'm just using the symbol for parallel there. Parallel lines, therefore no solution. They will never cross. So there's no solution to that system of equations. Okay, the last system, if we take the first equation and rewrite it, we get negative 4y equals negative 10x plus 8. We bring over the 10. X to the other side, it becomes a negative 10x, and we divide by negative 4. Divide by negative 4, by negative 4, and we're going to get y equals, if we reduce 10 over 4, well, the negatives are going to cancel each other out to make it a positive, and 10 and 4 have a 2 common factor of 2, so that becomes 5 over 2x, and it's 8 over negative 4, which is minus 2. So that would have a slope of 5 over 2 and a y-intercept of negative 2, so I'm going to just plot that there now. So negative 2 for the y-intercept, and up 1, 2, 3, 4, 5, and over 2. I can't go very much further there, so we'll just connect those. Then if we move to the other equation, we've got 2y equals 5x minus 4, so it already has the y term by itself, so all we need to do is divide by 2. And if you look at this form now, you see that is exactly the same equation as the one we just did. So that means that those two linear systems are exactly the same. So the same lines, therefore infinitely many solutions. Everything is a solution because they represent the same line. So no matter what x you put into the first equation, x and y you put in the first equation, that's a solution to the first equation, it will also be a solution to the second equation. So that leads us to this summary here, which basically says that you should have noticed that there are 3 possible results you could have. You could have lines crossing over and meeting in one place, at one point of intersection, or you could have parallel lines which would never meet, and therefore there'd be no solution, or you could have 2 lines representing the exact same equation. So that would be infinitely many solutions. Okay, so this next example is basically using a linear system graphing a linear system to demonstrate or model a situation. So it says, Kelly left Mount Pearl at noon to travel 700 kilometers to Corner Brook for a swim meet. Craig left Corner Brook at the same time to travel back home to Mount Pearl as he was finished his time trials for the same swim meet. Kelly's average speed was 95 kilometers per hour, while Craig's average speed was 90 kilometers per hour. A linear system that models this situation would be d equals 700 minus 95t, and the other equation would be d equals 90t, where d represents the distance in kilometers from Corner Brook, and t is the time in hours since the cars departed. So Kelly's equation would probably be the first one because her distance is 700 kilometers at the start. So when time is 0, she would be 700 kilometers away from Mount Pearl, and that would be the equation D. When you plug t, time equals 0, you will get 700 kilometers away from Corner Brook is 700 kilometers away from her starting point. Whereas Craig is starting from Corner Brook, so his distance from Corner Brook will be 0 at time 0. So this would represent Kelly's, and this one should represent Craig's. All right, so it says to graph the linear system on the grid, and can you explain the choice of the scale on the axis? Well, basically we need to have the distances or the vertical axis going up to past 700 just so that we can show Kelly's starting point. And the times, though, which would be on the horizontal axis, don't need to be as high numbers because it's not going to take too many hours to get from Corner Brook to Mount Pearl or Mount Pearl to Corner Brook. So it's only going to, 10 should be a sufficient scale for the 1 to 10 should be sufficient values to put on your time axis. All right, so we're going to graph the linear system. So the first one for Kelly's, our d equals 700 minus 95t. We would have our y-intercept would be 700, It's going to be kind of difficult to do a slope of negative 95 over 1 for this particular graph, so it might be easier to do a little table of values for this particular situation. So if we pick some values for the first equation, I'll call this equation 1. So we know that at time 0, it is 700. This would be your time. This would be your distance. And then at time, we'll just put some nice numbers in there. So at time 2, we don't need to do every single one. Time 2, we have 700 minus 95 times 2, which would be 510. And then at time 5, we would have 700 minus 95 times 5, which would be 225. So we'll plot those. 700, 0, 700, 2 with 510 would be about right here. And 5 with 225 would be about right here. So if we connect those points, we'll get a fairly good representation of Kelly's path. And then if we do, so this would be equation 1, and if we take Craig's equation, we have time and distance. And again, you can use the slope-intercept method if you want, but it's probably going to be hard to do the rise of 90 over a run of 1 when your scale is not going up by 90s. So it's easier probably to do table values. So if we know that time 0, he's at 0, and time 2, he's at 180, and we'll do the same values we did over there, I guess, doesn't matter. Time 5, he's at 450. So 0 at 0, start. 2 with 180. 5 with 450. Which would be about there. And then if we connect you can see, well, he would go up to 700, I guess, 700 kilometers around there. Okay, so it says use the graph to determine the point of intersection. And so right now you can see that graphing is not always that great, especially when you're doing it by hand, because we, like in the last ones we did with the slope and y-intercept, they always crossed over at a point that we had used on both graphs. But in this case here, it's not crossing over exactly the point that we used on to draw the graph, and where my lines are so squiggly, that's even harder to read the graph here. So based on where mine are crossing over, which is around here, it looks like it's about 3.8 and 350. So approximately 3.8 and 350 kilometers is when they would basically pass each other, I guess. So the x-coordinate represents the time they meet, or they might not actually meet each other, but they will be in the same spot at the same time. What does the y-coordinate represent? The y-coordinate represents the distance. From Corner Brook at the time they meet. Okay, and the next question asks us, is our answer exact or approximation? And we would definitely say that ours is an approximation because they aren't exact coordinates. And if you were using technology to graph, you'd be able to zoom in and get the exact answer, or pretty close to a more accurate answer at least. So we want to check to see if, I should just go back and plug those values in to our equations. If we go back and plug in 3.8 into the first equation, I forgot to label this one too. So 3.8 into the first equation, 700 minus 95 times 3.8. So 95 times 3.8, and then subtract that from 700 gives you 339. And then if we put into Craig's equation, 90 times 3.8, we get 342. So we're pretty close, but not exactly, because they're not giving you the exact y coordinate. So it is an approximation. Okay, so we plug them in. Like I said, you can see that they're not both giving you the exact same y value. If you want to write that down, you can. That when you substitute the time into each equation, distances are very close, but not exactly the same. Okay, one was 339 and the other one was 342. All right, next example is Kobe Bryant. On October 10th, Kobe Bryant scored a season high 40 points. His 40 points were scored on 1-point free throws and 2-point baskets. He made a total of 25 shots. So write a linear system to model the situation and define the variables used. So we would be looking for the number of 1-point free throws and the number of 2-point baskets. So we'll say F equals number of free throws and B equal number of baskets. So we have to come up with two equations now, because those are the two things we don't know. So it says he scored a season high 40 points, and his 40 points were all scored on the 1-point free throws, 2-point baskets. He made a total of 25 shots. So that would mean that F plus B would have to be equal to 25. And then the other equation would have to come about the points. So every free throw is worth 1 point, so that would just be F. The number of free throws is the number of points you get, plus, but you get 2 points for every basket, so it'll be 2 times every basket, and that should give you a total of 40. Okay, and the other equation was F plus 2B equals 40. So if we have to graph this, we have to decide which one is going to be our dependent, which one's going to be our independent, and it might be easier to write both these equations with the F by itself. So that would be, F would be our dependent. So F is negative B plus 25 would be the first equation. And the other equation, to get F by itself, we just write that as negative 2B plus 40. And looking at the types of values that we have here, we know we're going to have to go up as high as 40 on the dependent variable axis. And we need basically the number of points together. Number of throws was 25, so we need to probably have at least less than 25, but no more than 25 on the independent variable axis. So let's try a scale of 5, 10, 15, 20, 25, 30, 35, 40. Yeah, we'll go 5s probably. So every second one, 10, 20, 30, 40, 50. And then on this one, we'll probably just go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So our dependent axis, we're using F, and our independent axis, we're using the B's. So if we graph each of these equations now, so the first one there has a y-intercept of 25 and a slope of -1. The coefficient in front of the B coordinate, the independent coordinate, is -1. So our scale on our x and y axis is not the same. So it would be kind of, if we actually took a slope of -1, that would be from where we are here, 25 down to 20, that would be 5. So we would have to match that up with 5 to the right. And then down 5 and 5 to the right. And looking at our scale, 1 block down is 5, and 2.5 blocks would be 5 to the right. So we connect those points. That would be our first line. Also hard to draw a straight line, sorry. And the next equation has a y-intercept of 40. And the coefficient in front of your B is -2, so that's a slope of -2, or -2/1. So if I go down 10, then I'd have to go right 5. Down 10, which would be 2 blocks, and right 5. Down 10, which would be 2 blocks, and right 5, which would be 2.5. Around there. So the next graph would have an equation. Next equation would have a graph, something like that. So this is our equation 1. This is our equation 2. If you want to label them, this graph is equation 1, and this graph here is equation 2. So question C asks you to use the graph to determine the point of intersection, and our point of intersection appears to have coordinates of 15 and 10. So the 15 would be, in this case, our x's are B values, and our y's are actually F values. So our coordinate for B would be 15, and our coordinate for F would be 10. So what does the x coordinate represent? That represents the baskets. X coordinate is the number of baskets and the y coordinate would represent the F value, or the number of free throws. So in the game, where he scored 40 points, he got 15 baskets and 10 free throws to score the 40 points in a total of 25 shots. So just write 15 here and 10 here. Okay, the next example talks about 2 different taxi companies which charge different base rates to collect passengers and different travel rates for each kilometer, as displayed in the table below. So the first question asks you to write a linear system to model this situation and define the variables used. So if we look at the information, one taxi company is Avalon Cabs. It has a base rate of $3 and an additional per kilometer charge of 50 cents. So that basically means they're charging you 50 cents a kilometre on top of the $3 base rate. And Bjorn Cabs charges 40 cents per kilometre on top of the base rate charge of $5. So if we're just going to use K for kilometres and C for charge, we would have K equal the number of kilometres and C equal the charge. Okay, so the linear system to model the situation that we are asked to write, we would use, for the first company, Avalon Cabs, the charge is 50 cents, so write that in dollar format, decimal 50, kilometre plus $3, and the other company would have a charge of decimal 40K plus $5. And again, because these equations are written in, they're in slope-intercept form, but instead of having y and x, we got c and k. But the slopes are in decimal format, so you can either change the decimals to fractions, or you might just want to do a little short table of values. You only need a couple of points to graph a line. So if we do for the first equation, a little quick table of values, we've got k values and c values. It's a good idea to just do a few points so that you know how you're going to scale your x and y axis, or dependent and independent axis. So if we start off with a charge of 0, your base charge, you'd get $3. And because the kilometre charge is 50 cents a kilometre, let's use numbers that are basically even numbers, so that we can avoid using fractions and decimals. So if we have, for example, 10 kilometres, we would have a charge of $5 plus an extra $3 would be $8. And then if we do a little, again, get a couple of points to help us graph the line, because we only need 2 points to graph a line. And for equation 2, our k and c values, we'll start with our base charge of 0, goes with 5. And again, if we use a nice number like 10 for kilometres, we can get rid of that decimal, so it'll be 10 times decimal 40 would be 4, plus 5 would be 9. And we can pick some more points if we want, but let's just try a few of those. So we want to go on the kilometres. We can probably try to put in 2, 4, 6, 8, 10. And for the costs, we want to go up at least as high as probably 10 as well. So we've got 2, 4, 6, 8, 10, 12. And then when we plot our points, we've got 0 goes with 3 for the first one, 10 goes with 8. So that graph looks something like that. And that would be equation 1. And then the other one would be 0 with 5 and 10 with 9. So you can see that when we draw that, they don't have the same slope, but they're not crossing over yet. So we can see that our x and y scale that we've chosen is not enough. So we're going to have to go back and take some more points and try that again. Because we're not seeing our point of intersection. So if we go back and take, say, 20 in our table, 20 in the table, 20 would go with $10 plus 3 is 13. You put in 20 for k in the first equation, and 20 in the second equation would go with 8 plus 5 is 13, and there is, you know, that's the point of intersection there, because you got the same point on both. So if we go back now, we know that we have to get the point of intersection to show up, we need to go at least as high as 20 on the x-axis, or k, in this case they're k's, and our dependent are c's. So a good way to label or scale the k-axis, the independent axis, might be in units of 5, and I'm going to put every 2 blocks 5, so that would be 5, 10, 15, 20, and 25. And then on the dependent axis, which is representing charges in this case, I'm going to go up, basically just label every second one. 2, 4, 6, 8, 10, 12, and 14. So you will get your point of intersection shown up there because we know 2013 is on both equations. So if we graph the line 0, 3, first line has coordinates 0, 3, 10 with 8, and 20 with 13. And if we connect those, looks something like that. So equation 1. And then equation 2 is 0 with 5, 10 with 9, and 20 with 13 is also on that graph. And so these ones would cross over. Oh, my labels are kind of on top of each other there. So we've got equation 2. That doesn't look, you can't really distinguish which one is which there, so let's try that again. So this one was equation 2, and this one was equation, this one was equation 1, the bottom one. Okay, so use the graph to determine the point of intersection. Now, we just happened to do our table of values that we could tell what the point of intersection was from the table, but our graph shows it as well, that the point of intersection is 20, 13. And what does the x-coordinate represent? In this case, the x-coordinate represents the number of kilometers, and the y-coordinate represents the charge. The charge for when the kilometers are the same on both taxi cab companies. So therefore, the point of intersection represents the number of kilometers for which both companies charge the same fare. And looking at that graph too, even though it's not, it doesn't ask you there, you can tell from the graph which company would be better to go with, for depending on the kilometers you're driving. For example, the company 1, if you're driving up to 20 kilometers, is actually cheaper than company 2's graph, which is company 2 is Bjorn Cabs. So Bjorn Cabs, and I forgot to label the equation over there. So Bjorn Cabs would actually be cheaper though, because the line, when you look at the lines, the first line is the lower one up till 2013, and then it's the second line that becomes lower, the lower charge, which is Bjorn Cabs is cheaper if you're going more than 20 kilometers. Now, there's some questions there on page 408 for you to try, just to practice some graphing. The questions, as you can see, we didn't assign too many that were like the last couple of examples we did, because it is very tedious to solve by graphing in this way. And as you saw with that last example in particular, sometimes you might not get the point of intersection, then you got to erase your graph and try again until you scale your axis in a way that you can get the point of intersection in there. So graphing is not always the best way to do it. So we've only given you some exercises there that are just graphing just straightforward lines. When we get to word problem types like this, sometimes it's better to do an algebraic method first to help you find a solution rather than try to graph, unless you got technology and it's not too time consuming. So that's it for section 7.2.